Hello everyone, in this video we'll discuss about the Coulomb damping. Now damping is what? It is the method or the device used for the energy dissipation in the system by means of heat or noise. And there are different ways of damping: viscous damping, in which the fluid was used as the damping medium, and the second type of damping is the Coulomb damping, in which the energy is dissipated due to the sliding friction, or we can say whenever two parts they rub against each other, Coulomb damping takes place. There is another type of damping, that is the material damping, which occurs between the grains of the materials, right? So in this video we'll discuss about the Coulomb damping, which is caused because of the sliding friction. Now this type of damping, it finds its applications. You can take the example of the airplane wings. So what exactly happens? The energy is being dissipated constantly, and why? Because of the sliding friction. So if there is a let's say a mass that is sliding on a surface, so because of this sliding friction, what is happening? The dissipation of energy is taking place continuously, but the sliding friction is what? It is a constant value. What is friction? It is mu n. So this is what? This is a constant value, and this sliding friction, it is independent of the surface or the area. It is independent of the velocity and the position of the object, and the object, it keeps on vibrating to and fro unless the whole energy dissipation takes place and the body comes to the rest. And we also know that the direction of friction is always in the direction opposite to that of the motion. So what happens if the body is moving, let's say, in this direction? So friction will act in the opposite direction and vice versa. So because of this sliding friction, what will happen? The amplitude of the motion, it decays with time. So if, if initially, let's say, this is the amplitude of motion, because of the friction, it what happens? It decays with time, and this way the dissipation of energy takes place in case of the Coulomb damping. And also if we plot a graph between the force, so let's take the force on, let's say this is the on x-axis, if we take force, and if we take, let's say, the acceleration, because this is what? This is opposite to mass and acceleration. So let's say if we take acceleration, or maybe velocity, because the change in velocity is creating acceleration. So what type of graph we'll see? So the force, the value of force will remain constant, or you'll say it remains unless what happens? It reaches a limiting friction value, and then the acceleration takes place, or you can say the displacement takes place, right? Similarly, if we go in the opposite direction, what happens? Unless we reach a limiting friction value, there won't be any movement in the body, and once that value is reached, what will happen? The displacement will take place. So let's take the plot between the displacement and force. So the limiting friction, because of the limiting friction value, what happens? The motion will not start unless we reach the value f, and after that the motion starts linearly. So we'll make a lumped parameter model which consists of mass, which is the inertia element, spring, that is the restoring element with spring stiffness S, and the energy dissipative element, that is the Coulomb damping, in which we are using the solid friction, and this element is showing the friction which is causing the dissipation of energy. Now what exactly is happening? The force is being applied to this device, and force, we have already discussed that this force should exceed the value F of the limiting friction, right? And below this value F, what will happen? The force, it keeps on adjusting itself unless we reach the limiting value of friction. So what exactly is happening with this mass or with this body? It is having to and fro motion. So we'll take up the cycle of a to and fro motion in two parts. Firstly, we'll assume that the body or this mass is moving in the left direction or in this direction, and in the second half of the cycle we'll assume that the mass is going in the other direction, right? So the first step we'll do is to draw the free body diagram. So in the first half of the cycle, if we see that the mass or the body, it is moving in this direction, so the velocity is in this direction, right? And of course the spring stiffness, the restoring force, it will act in this direction, and we know that the acceleration, it will always act in the direction opposite to that of the force, right? So the acceleration will act in this direction, and we are saying that the velocity is less than 0 because it is in the negative direction, right? So if we equate all the equations, or if we balance all the forces acting on the body for the first half of the cycle, we say that if body is moving in this side, that means the force or mass into acceleration is in this side. So this is m into acceleration, which is x double dot, is equal to frictional force minus the spring force, which is because the direction of spring force is opposite to that of the frictional force. So this is the equation we get. If we take all the factors on the other hand, we'll say that mass into acceleration, or the force, plus the spring force, which is Sx minus frictional force, because we can see that the direction of frictional force is opposite to that of the movement of the body and the spring force. So this has to be equal to 0. So this is the equation that we are getting for the equilibrium position. Now in this equation, what we are going to do, we are going to apply the initial conditions, right? If we plot a graph, so we say that at time is equal to 0, what is the position or what is the displacement? Let's say the displacement is some value x1, right? So initially, let's say that we are beginning the cycle with some initial displacement, that is x1, and initially the velocity is 0, right? So when we will be using these initial conditions, so this is the equation that we derived, and we can write this equation in this way. We can take spring stiffness as common, so equation will become mass into acceleration plus s, that is spring stiffness, x minus f upon s, which is equal to 0. Now we can convert this equation in terms of another factor, which is y. So we can say that x minus f upon s is y. So what will happen? X double dot, which is x acceleration of the body, will be equal to y double dot, right? So we can replace this equation with this equation. So it becomes m into y double dot plus s, because this factor we have taken as y. So plus sy is equal to 0, right? So this is the equation for simple harmonic motion. So the solution for this equation can be given as y is equal to a sine omega nt plus b cos omega nt. And omega n is what? The natural frequency of vibration, which is given by under root s upon m. So if initial condition says that x dot is equal to 0, so y dot is also equal to 0, right? And according to initial condition, what is x? It is x1. So the equation of y is x minus f upon s. So the condition for y becomes, because x becomes x1 in the initial condition, so y becomes x1 minus f upon s. So if we use these two equations, one for the displacement of y and one for the velocity of y, which is nothing but the differentiation of y. So what is velocity? It is rate of change of displacement with respect to time. So if we differentiate this equation, we get y dot is equal to a omega n cos omega nt minus b omega n sin omega n t. So if we place these two conditions, we'll get the value of the constants a and b. So when time is equal to 0 and y dot is equal to 0, we get 0 is equal to a omega n. So a is 0 and b is x1 minus f upon s, right? So when we place the values of the constants in this equation 1, this is what we get, which is y is equal to x1 minus f upon s cos omega nt. And if we want to find the velocity, so it will be y dot, that is the minus x1, because the differentiation of cos is minus sine, right? Minus sine theta or minus sine omega nt. So it will be minus x1 minus f upon s sine omega nt into omega n. So this was the initial condition when theta was is equal to 0 and we got this value. So what will be the next time when sine omega nt will be equal to 0? It will be 0 when omega nt will be equal to pi, right? So because see, the initial condition for velocity we took was 0. So next time velocity will be 0 when this condition, this equation will be 0, and it will be 0 when omega nt will be equal to pi. But what will be the displacement in that condition when the angle is pi, or when omega nt is pi? It will be x1 minus fs cos pi, and cos pi is minus 1. So the equation will be negative of x1 minus fs. And we know what is y. Initially we assumed y to be this x minus f upon s, right? Displacement minus f frictional force upon s. So when we equate these two equations, we find the value of displacement as minus x1 minus 2f upon s. So that means what? We started from some equilibrium position and now x has moved to a negative value, right? And also the amplitude has decreased. So if we see in the graph, we'll see that when we started from this condition where the displacement was the maximum, which was x1 at time is equal to 0 and velocity is 0, what exactly happened? The amplitude decreased to a negative value, which is minus. So because negative is the negative, it is in the opposite direction, so the value becomes x1 minus 2f upon s for the first half of the cycle. So in first half of the cycle, the body goes from this equilibrium, or you can say the mean position, to a new position on this hand. Now because this is a to and fro motion, after going to this position, what exactly will happen? The second half of the cycle will start. So for second half of the cycle, the body is moving in this direction. That means the velocity is greater than 0, or we can say the velocity is increasing. So it is in positive direction. So the body, the velocity is in this direction. So acceleration will obviously act opposite to that of the motion. So it will be opposite to velocity and the acceleration of the body, and the spring stiffness will act in this direction as it was acting for the first half of the cycle. So the equation becomes mx double dot, which is mass into acceleration. So here we are using the Newton's second law of motion, is equal to minus f, right, because they are in the opposite direction, minus s into x, right? So that is the spring force. So if we take these factors, so this is the equation. So if we take these factors, it becomes this equation, which is mx double dot plus f plus sx is equal to 0. And if you compare with this equation, the equation remains the same, only what changes is the direction of friction, because the direction of motion of the body has also changed. Now for the second cycle is starting from this position, right? So what exactly are the initial conditions? We say that this is some other time period, right? This is some initial condition, some other time period, let's say which is t naught, it is 0. And what is x? It is minus this value that we calculated here, because this is here the first cycle stopped. So second cycle will start from the same point or from the same position. So it becomes minus x1 minus 2f upon s. And we also discussed that we were looking for the position where again the velocity will be equal to 0. So again for this the initial condition is that velocity is equal to 0, right? So similarly in this equation we can write it this way. If you take s common, it becomes mx double dot plus s, x plus f upon s is equal to 0. And let's assume that x plus f upon s is denoted by a term z. So the acceleration for z will be equal to the initial acceleration, or you can say that z double dot is equal to x double dot. So this equation can be written in this form, right? And because this is the equation for simple harmonic motion, we can write its solution as z is equal to c, because we have already taken the constants a and b. So we'll name the constants, let's say c and d. So it becomes c sine omega n t naught plus d cos omega n t naught, right? And the velocity will be this z dot will be c omega n cos omega n t naught minus d omega n sine omega n t naught. In equations 3 and 4, when you'll apply the initial conditions, right? The initial conditions, these are the conditions that we are assuming. So we'll get the value of the constants. So D will be equal to this, which is minus x1 plus 2f upon s, and C will be equal to 0. So when we place the value of these constants in equation number 3 and equation number 4, we get these two values, right? So the displacement Z, in terms of Z, will be minus x1 plus 2f upon s cos omega n t naught, and the velocity will be this, which is my negative of x1, because differentiation of cos gives minus sign. So it is minus x1 plus 2f upon s sine omega n t naught. So the initial condition said that the velocity is equal to 0. So next time again velocity will be equal to 0 when omega nt will be equal to pi. So if we place the value of omega nt not as pi in this equation, what it will become? It will become z is equal to minus x1. So, okay, minus x1 plus 2f upon s. And we assumed initially that z is equal to x plus f upon s. So when we place this value, we get the displacement as minus x1 plus 3f upon s. That means what this displacement is showing, it is actually showing the amplitude of the uh, oscillation or the vibration. So in this case, if this value is, see, this value has reduced. Initially it was x1, it reduced to x1 minus f upon s. Now for the next cycle it will reduce to x1 minus 3f upon s, and for the end of this cycle it will be x1 minus 4f upon s. So in this way you can calculate the values of the amplitudes for the cycle, and after some time period it will completely stop or it will completely decay. So this is what, this is the energy dissipation, and what is happening, the amplitude of the vibration, it decays with time. So this is what the graph says, that if we plot a graph between the displacement and time, so what exactly is happening? With time the displacement is decaying, right? Displacement is decreasing in, and the body comes to rest, or you can say in other words the energy is completely dissipated in form of heat or noise.